We'll be looking at question 22, June 2023 paper. In this question, it's a question on transition elements, which is the last topic of Unit 5. And we'll be exploring some of the chemistry involved. This is a nice all-rounder question. Let's have a look at the question. This question is about D block elements in period 4. D block elements in period 4 from scandium to zinc. So if you've got your periodic table at hand, it'll be good to refer to. Explain with examples what is meant by a D block element and transition element. Explain why some D block elements are not transition elements. There's a key distinction. It says use electron configurations to support your explanations. So as we can see, how many marks is this worth? This is worth a 6 mark. Now, the psychology of a question like this, students will immediately panic and think, what kind of question is this? But if you break it down and highlight it, or in the case of the exam, underline or circle, you can then start extracting the key points. Now, you see, if you look at the first line of the question, what is meant by the terms D block element and a transition element? These are definition questions. Now, a D block element, let's use a small d. A D block element which has the highest energy electron in the D subshell. That can be any element from scandium to zinc, any element including and between those two elements. Now, a transition element, there's a bit of a key difference here. A transition element is where it forms one or more ions. This is the key bit coming up now, with an incomplete D subshell. And we'll have a look at some examples. Incomplete or partially filled. Yep, you could, any one of those two terms you like. Partially filled. Now have a look at some examples. It says explain why some D block elements are not transition elements. Now let's have a look at. So examples of this, the ones that are not D block elements, transition elements, scandium and zinc are not transition metals, transition elements. Now, why is that? If you look at scandium, scandium has only has a 3+ ion. And if you look at the electron configuration of scandium, it's 1s2, 2s2. That's the full electron configuration. Now, if we look at if we were to remove 3 electrons, that would give us, take 2 electrons from the 4s subshell, that leaves only 0 electrons in the D subshell. The D subshell is now empty. It is not a partially filled D subshell. It's completely empty. This way, not making scandium not a transition metal. Now, zinc is the same. Zinc has a 2+ ion only. And if you look at the electron configuration, what you've got, the ion will lose the 2 outermost electrons, which is the 4s electrons. And here, the 3d subshell is completely filled. It's completely filled, it's not partially filled. And this eliminates zinc as a transition metal. So you need to know these 2 examples. What else do the questions say? Now, let's give examples of a transition element. Let's use, wait a minute, here. So an example we could use is, let's look at the periodic table. Choose one in the middle if you want. Let's choose an example of generally of a D block element. You got iron. Let's look at the atom. We're using iron. Let's put the electron configuration here. So Eg, let's do Fe. Now the atomic number is 26, 1s2. Actually, you know what? Before I explain this, let me just go back a step. I just want to explain one thing here. This does cause confusion. Even though the 4, let's look at the zinc, if I highlight it here. Let's look at the electron configuration here. Even though the 4s subshell is filled before, and you write it in numerical order right at the end after 3d10, but it's filled before. It's filled before, but when it becomes an ion, it's removed first. Those electrons are removed first. So just so that you don't get confused with that, the 4s electrons fill first, but they are removed first when an ion forms. Just something to bear in mind. Going back to the electron configuration, we're using iron, for example, has atomic number of 26. So we'll write down 1s2. So we've got 18 electrons here, 19, 20, and 26. That will be Fe iron electron configuration. Now, iron is also a transition element. And why is that? Let's choose one of its ion. Let's look at the Fe2+, which we've seen examples of. It's going to be the same electron configuration. And the 4s2 electrons are removed. So this leaves it with a partially filled D subshell. And having a look at the mark scheme, this covers all the marks, 6 marks. 2 marks for the definitions, up to 3 marks for the electron configurations, and then the explanation of why zinc or scandium is not a transition element. 6 marks over there. Moving on. Describe precipitation reactions using either copper or chromium as examples. Now, with this question, great thing about this question, it gets us to explore quite a bit of transition element, the chemistry involved. Now you see copper, let's use, we'll try to use both. Actually, we'll do both. Let's do both of them. Now, if we react copper, and first of all, any transition element, when we react it with sodium hydroxide, it gives us a precipitate. So let's react copper 2+ ions with sodium hydroxide. We're concerned with the hydroxide ion. And this goes on to give us the precipitate of copper 2 hydroxide. Now, in this equation, they've told you that this is a precipitation reaction, but usually you are required to give state symbols and make sure it's balanced. You're trying to balance the charges of the formula. This would be for copper. And also, you want to give the observation. The observation of seeing this, it will give you a blue, sometimes referred to as a pale blue, precipitate. You must give the color. You must give the color. 1 mark for the color, 1 mark for the equation. Now, if we were to, there are some other examples here, and using this opportunity to present them, you see copper 2+ ions also react with iodide ions. This is an equation that you need to learn because it comes up in redox titration when you're reacting iodine with thiosulfate. So when you react copper 2+ ions with iodide ions, it's a redox. Actually, it's a special type of reaction. Iodine is being reduced and oxidized. So it's a disproportionation reaction. So this gives you copper 1 iodide, and iodine is formed also. And to balance, you put a big 4 there. And what happens, it's not asked in this question, but a precipitate forms, a white precipitate, and the rest are aqueous. And as I said, this gives you a white precipitate. You need to know the colors, white precipitate. There is an example of chromium. Now, chromium is a 3+ ion. It reacts with hydroxide ions. It gives you CR, OH, and then a 3. Remember, it's a 3 because we need to balance with the +3 charge. And again, this question isn't asked, but in future, most questions tend to require these state symbols. And the color of the precipitate is actually gray, green precipitate. And again, as we're here, this is a bit of an add-on. As we're here, if you were to add excess sodium hydroxide to aqueous chromium 3+ ions, what you get, this precipitate actually dissolves in excess hydroxide ions, which gives you CrOH 6. This becomes aqueous. And the charge of the whole complex is a 3-. And you've got your state symbols, S, aqueous, and aqueous. Yep, so you've got a range of possible answers here, but something great learning experience here, looking at all the possible answers. Now, moving on. Describe ligand substitution reactions using either copper or chromium. Let's try to explore both. Now, copper, the complex in water is surrounded by 6 water molecules. What is a ligand? A ligand is a molecule or an ion that donates a pair of electrons, forming a coordinate bond. In this case, it's the lone pair of electrons on the oxygen that forms that coordinate bond with the transition metal ion. Now, there's 6 waters. Copper's a bit of an exception. It only substitution only occurs with 4 of them. For the rest of the examples, it tends to be 6. And this gives you the complex of Cu. 2 waters are remaining, and the others are ammonia. Just make sure it's balanced. And also, they expect you to give the observations. So what happens So in this, I forgot to put the charge in. From a blue precipitate, from a pale blue solution, it goes on to form a dark or deep blue solution. From a pale blue precipitate. Learn these colors. I believe you've all seen the OCR poster with all the colors and observations for transition. It's like a yellow, format chart. Learn all the colors. 1 mark for the equation, 1 mark for the color in this case. Your other examples, you've got, let's try with chloride ions. You get copper, if you react with concentrated hydrochloric acid, those chloride ions go on to form a copper chloride complex, CuCl4, with a 2- charge, and all those waters are given off. And you see the coordination number, or the number of coordinate bonds, goes from 6 to 4 in CuCl4. Now, that's to do with the size of the chloride ions, as well as the charge. It only allows for 4 chloride ions to surround it. And the color of this, it goes from it starts off as a blue solution. It goes from blue solution, and it turns into a green, then it goes into eventually a yellow. Oops, you can't see yellow there. Yellow solution. As I said, learn the colors. So giving you 2 possible answers there. The last question is asking you, waiting for time. Okay. The ethane di-O8 ion is a bidentate ligand. Bi meaning each ligand forms 2 coordinate bonds. Dentate, you can think of like teeth, 2 teeth, or 2 tooths. A complex ion of cobalt-3 contains 2 ethane di-O8 ligands and 2 water ligands. Determine the charge of this complex ion and the coordination number of the cobalt in the complex. Charge of the complex ion, the whole complex ion, is going to be, so you've got cobalt, let's work this out. Cobalt is +3, and you've got -2, you've got those 2 ligands there, and the others are water. So +3 -4 is going to be -1. That's your charge of the complex. What is the coordination number of cobalt? You see, you've got 2 ethane di-O8 ligands. So each of them have formed 2 coordinate bonds. So you've got 2 times 2 here, and you've got 2 water ligands. Water is a monodentate ligand. It only forms 1 coordinate bond each. So 4 + 2 gives you 6. I'm tempted to draw the complexes, but I think, I don't know. Let's see how we go. Let's do this last question. We maybe come back to try drawing those. This is a redox titration equation, and redox equation. These questions tend to be very poorly answered. Let's break this down. We're going to convert the words from the question and form an equation. Construct an overall equation. Let's have a look. An acidified solution containing dichromate ions reacts with vanadium 3+ ions in a redox reaction to form a solution containing Cr 3 plus, and VO2 ions. Construct the overall equation. Let's see what this is. So you've got acidified dichromate reacts with vanadium, 3 plus ions, V3 plus, and it goes on to give you Cr3 plus, and it gives you VO2. You see, where do the hydrogens go? We can assume it would give you water. Now, we need to look at the oxidation numbers. Each chromium is going to be plus +6. How did we work that out? Each oxygen is -2. That's -14. 2 chromiums is +12. Each chromium is +6. It goes from +6 to +3. It has gained, if you look at the 2 chromiums, they have gained 3 electrons each. So that's +6 electrons. Vanadium has gone from 3 plus oxidation number to a +4. Vanadium has lost 1 electron. So we need to balance those electrons. How do we balance them? One is gaining 6 electrons, and the other is going to be only losing 1 electron. We need to balance that, so we put a big 6 there. +3 to +4. The mark scheme is saying something else. What's going on here? So I've read the question wrong. Aha. Look, there's a plus sign here. That's the mistake I've made. The plus sign means, look how easy it is to lose a mark. You see, the VO2 has a +1 charge. That means each oxygen, if it's -2, that's -4. Vanadium must be +5. +5 -4, yeah, gives you +1. So here, from +3 to +5, vanadium is losing 2 electrons. That makes a bit more sense. So what's going to happen? Vanadium, so yeah, we need to multiply this by 3 to balance the electrons. Once we've balanced the electrons, ladies and gentlemen, we just balance everything else as you would do normally. 2 chromiums on the left, let's put 2 on the right. Oxygens, there are 6 oxygens here. 3 times 2 is 6. And you've got your 3 times 2 is 6. You've got 1 oxygen here. That's 7. So the oxygens are balanced. And let's put a big 2 there to balance the hydrogens. And if we have a look at the mark scheme, 3 plus, 3V3 plus, dichromate ion, 2H plus, 3VO2 plus, 2Cr, yep. And that is correct, ladies and gentlemen. That is the end of this question. And I'm going to try squeeze in a quick question. You know, this question here, they could very well, let's give you what other questions they could ask you. they could ask you, this can give rise to optical and cis-trans isomers. And if we draw this, what's the transition metal ion? Cobalt 3+. So you've got CO, and you're going to have a coordination number of 6. This is a possible question the examiners can ask you, so I thought I'd use the opportunity to squeeze it in. So the optical isomer would be ethane dioate. Ethane dioate. Let me just. So dioate, let's put the oxygens here. Draw the skeletal formulas. Oxygens here. And you've got your chloride ions. And the charge of this complex would be, cobalt is 3+. 3+, actually we answered this question. The charge of the complex +3. Sorry, this is not, this is water. And it will have a plus charge. And if you do the mirror image of this, that will give you the optical isomer. Now the cis-trans version would be where the water, if you swap this water and put it here and turn that bidentate ligand to the other side, you'd have the trans version of that isomer. At the moment, the waters are together, so that's cis, and you can get trans, which will be across the molecule. We will see more questions like that coming up in the near future. Otherwise, I'll cut this video now, ladies and gentlemen, and I'll see you next time.